many things that can best fit into a specific one. Any questions about that? All right, the good stuff is coming soon, I promise you. Question up front.
Can you say a couple of words about multi-byte structure? Pretty much the same as one byte symbol? Or
I'm sorry, I don't quite understand.
I'm just a little confused. Originally we have one byte.
Mm-hmm.
We use ASCII.
Yeah.
And then it was we started using multi-byte.
Mm-hmm.
Or went to Unicode.
Mm-hmm.
Why multi-byte were necessary?
I think because, and this would be an exercise for the historians rather than the engineers, but I would say probably because Unicode was something that required a dedicated standardization effort. It was something that took a while to get going. It's much easier from if I got to get more characters in there to just put that multi-byte character in, set in there to have that work. I mean, it was something that was quick and dirty and allowed for you to expand your encoding space. But it wasn't something that was designed to be used across all languages, across all platforms for the rest of time. Any more? All right. So in the Linux, Unix, every Nix world, general assumptions are a little bit harder to make. There are a couple of standardization efforts, and obviously the POSIX locale offers some standardization. A lot of times you'll see that there'll be support for core UTF-8 by default on many of the distros. It's not something where you're going to be able to make as many, set statements like everything will become UTF-16 when it gets down to the system layer, because it is going to be very configuration specific. And the effect of that is it really pushes internationalization up the stack. If the platform doesn't act as, if the platform doesn't act with the same by default behavior, then the application developer is going to have to do more to integrate internationalization in, and that's going to be something that's going to make things very, application specific. So, for example, if you go to a lot of the internationalization support websites for Linux, you're going to see things on, here's how I can use a shell that will by default support, Japanese characters, or here's how I can use an editor that supports by default this code page. And that's something that's going to be, when you're attacking these systems, you really have to understand a lot more about the application you're attacking because it is going to be specific. This is good and bad because without the pixie dust internationalization happens approach, if you have internationalization in your application, you pretty much really want it to be there. You must know what you're doing, or that might be a stretch, but you must know that there's something to be done and you're integrating a library or something that has internationalization support. Then again, anytime you explicitly do something like that, it's complicated, it's error-prone, often implemented insecurely. You have a lot of flaws. There are common utilities and libraries that offer support, like International Components for Unicode is an open source library that does all the conversions along the same lines as what we saw with multi-byte to WIDECAR and the reverse. IconV is a utility you'll find in most distros that will convert files between different encodings. libiconv is the same thing, but in a library form. And you can always roll your own because everybody else does, and please don't. And there's a couple websites you can check out if you want a bit more information on standardized internationalization concerns in the StarNix world. But everything else, support isn't just from the OS. Like I said before, it depends on the programming language you're using, or virtual machines. If I'm using Python, what I have to do to get a Unicode character in there is very different than what I have to do in Windows, or if I'm programming in C++ for Windows. And again, very different than what I'm using in .NET. Virtual machines, like those used with .NET and with Java, will also add another layer of core nationalization support where things have their own unique representation inside memory. And then you also have application-specific things, something that doesn't care what the OS or virtual machine provides, but it tries to make its own UTF-8 parser in there. So it is something that, even though there are varying levels of support from different platforms and libraries, it is something that you're going to hit in almost every application. And this offers a unique attack surface. We're talking about things that are based on standards. This is cross-OS or language, application class, implementation. If you're using HTTP, you have internationalization support, whether you know it or not. And so this really does hit almost every application out there. So for example, if I'm writing any application, my development platform is going to have some sort of internationalization support. My external libraries, anything I call into, same thing. Operating system, same thing. Application server, database server. Anytime I'm going off a machine, I'm going to have almost certainly some kind of attack surface or crossing an internationalization boundary. And of course, the client's at the end of the line. So with web applications, you have code page that can be set on every HTTP request, response, and in the header of the HTTP page. And there's 3 unique attack surfaces where I can start putting mismatch encodings or double encoding to get past things. A code page is set on the first line of every XML document. So if I'm talking over a web service to an HTTP server, I have the XML document, the HTTP request encoding, and everything coming back is different areas where I can perhaps specify a code page is other than what it's expected. With the old multi-byte to wide-car things, a lot of conversions will depend on your default code page, and that's what the CP/ACP stands for. So when you test these things, you really have to change your system and user locales and try testing on something that's a built up from scratch Japanese machine with Japanese databases and everything else, because you'll be surprised at how things behave differently when they act off of those different defaults. So if we're talking about a standard stack of a web service, you have an HTTP parser sitting on top of an XML parser and SOAP stack, sitting on top of your application logic. And this is where most people are writing their applications. You take in your data that's coming from the web service and you're sending it out to a database. That's usually the most practical point for people to control their input validation and check for internationalization issues. But even below that, you have your database access library. You have your ODBC and whatnot. You have your database, SQL Server. You have your operating system down there. Anywhere along the line, if somebody makes a mistake and allows manipulated data to pass through, then you have a potential issue. All right, and we'll see a couple of those in a moment. So that was the background. I tried to keep it quick, but if anybody has any questions, feel free to ask now. We'll get into some attacks in a moment. All right, must have nailed it. Historical attacks. Now, anytime somebody's asked me about my talk in the last few weeks, they've always said, so, like that NT4IAS thing. Internationalization has received some attention from the security community, and there have been public flaws along these lines. You can pretty much chalk these up as lessons learned. We saw those 2 APIs before, messing those up, the count of bytes versus count of characters, whether it's a 1 byte per character or 2 bytes per character. All that resulted in a bunch of buffer overflows, input validations, standard application attacks. And people, for the most part, now know that you have to use these APIs with a lot of diligence in order to prevent such attacks. It's in writing secure code and everything else that does that sort of thing, or that gives guidance on that sort of thing. Another thing interesting about, though, is that a lot of these behavior, in Windows at least, there's a lot of functions that depend on your compile time flag. So for example, if I use a tcar type, or if I use an elster star function, then these things will act differently whether you define with the Unicode flag or not. So you might test your application to death and find that there are no flaws when it's compiled without the Unicode specifier, but then when you do, you find buffer overflows all over the place. This isn't something as much of a concern if you're releasing a binary and send it out to the world, but if you're releasing open source software, you have to realize that that could be a change and test it twice. The big one, though, that everybody refers to is the non-minimal UTF-8 encodings in NT4IAS. So, abstracted, web server is just a thing that takes a request from the web, converts whatever was requested into a file name, opens the file, sends it back to the user. So typically I'll see, HTTP, web server, scott.com, and then go to my web folder and index.html. And people would look at that and say, hey, well, I want to get something outside of the web root, and I don't want to have, the index.html. I want to be able to pull down somebody's SAM or password file. So they say, okay, well, I'll just ask for the web root, .. whatever, one of those 2 things. Now, most people who are creating web servers realize that that's an issue, so they check for things like .. So here's where encoding comes in. I encode it as %2e, %2e, %2f, which that is the hexadecimal representation for period, period, slash. If somebody were validating and looking for it specifically for .. then that would get by it. If it were to be decoded later on, then it would go into the open file command, create file, whatever, and serve up the malicious file. So people thought, oh, even that, I'll decode it. I'll look for %2e, %2e, %2f. And then here's where the flaw happened. Same thing, but I say, instead of %2e, I say %C0AE. Now that's a UTF-8 encoding, which is of the same character, %2e, but UTF-8 can be between 1 and 5 bytes long. So instead of using the shortest representation, which is %2e, they used %C0, %AE. And this was something that the decoder did not check for, and so this allowed you to request any arbitrary file off of the disk with the web root. This is something that was fixed years ago, and at the Unicode Standards Committee said that if anybody else does this, then they cannot advertise themselves as Unicode compliant. So if you're by default, UTF-8 parser allows non-minimal encodings, you can't advertise yourself as being compliant, people lose money, so almost nobody does this anymore. Now what they do instead is going to be the subject of one of our attacks here in a moment. Any questions about these old attacks? Oh, that's outside. Okay, current attacks. So with the current attacks, your validation is performed on your input and then change the locale-specific text. So I'm reading in a Unicode string. This happens a lot in the standard newer platforms. So I'm a web app developer, I'm using .NET or Java. I'm almost always going to get a post parameter or a query string parameter as a Unicode string. So when I do this, when I read that in, I then convert it to something that's locale-specific, like Windows 1252 or ISO 8859-1. When it has that conversion, it's a many-to-one relationship like we talked about before. So we can have that apostrophe character, the apostrophe-like character, become an actual apostrophe. And here's one example. The Unicode code point 2032 is the prime character. So the prime character is very similar to an apostrophe character in look, but obviously not in semantics, and it has a lot of concerns within database applications. When it's converted to Latin 1252, without any kind of, don't best fit me, at least on Windows, it becomes hex 27, the actual apostrophe. Same thing happens with quotation marks, numbers, letters, etc. There's a number of things that are equivalent characters to apostrophe if you allow the conversion routine to give you a break. And Latin 1 isn't the only code page. Have you tried your Japanese web client lately? This is a really big concern for cross-site scripting attacks, where you can put up a bracket-like character, bracket script, but instead of an actual bracket that people tend to filter out, you put in something like it. It's interpreted by a Japanese client properly, but not by an English one. So let's take a little time for a quick demo. Anybody have any questions while I'm getting that ready? Okay. So here is a very simple web service in .NET called SQL Demo. It allows you to interact with it over this form here. It has 4 simple routines: log in user, log off user, print info, and update my information. We're really only going to mess with log on user here. And you'll see that it, let's see, can you guys see that all right? There we go. So it takes a very simple login. If I say my name is Stender, my password is Scott, and I invoke it, very strong passwords, I get a valid cookie back, which is 1,000. If I give it the wrong password, like Scott period, then I get -1 invalid cookie back. So now I figure that this logon user, like every other web application, probably has a database back in there with a users table, or does select star from users where name equals and password equals. So I'm really smart and I type in an apostrophe. And I type that, and I get a -1. Okay, so maybe not. However, we saw just a moment ago that Unicode code point 2032 is a somewhat equivalent character to apostrophes if you allow that conversion to happen. And so perhaps this service does a round trip, puts things down into Windows 1252 or 8859-1 or something else where there's that, where it might become an apostrophe. And it so happens, this right here, that is unprintable, is Unicode 2032. You can see it looks a little bit like an apostrophe, but it is not one. And if I type enter, then I get unclosed quotation mark. So again, we saw a moment ago that when I typed a simple apostrophe, the standard SQL injection test, we got nothing. But when we type in something that's similar, it got best fitted to an apostrophe, sent to the database, and now we have a pretty standard SQL injection exception occurring. So just to show you guys, I'm not lying here.